Okay. Yeah. Hi. Uh, Thanks for joining. And my talk is about scalable and continuous benchmarking on cloud FaaS platforms. And we have already heard the terms benchmarking and FaaS today in Tim's presentation. I'm kind of doing this the other way around. So we are using cloud FaaS platforms to benchmark just general all kinds of applications. And when we're talking about micro benchmarks, this is an example for micro benchmarking functions. And generally what you want to do is you want to take something that has about the size you would test in a normal unit test. And instead of calling it once, you call it a couple of times. And the Go micro benchmarking framework increases the number of times the function is called per micro benchmarking run until it takes 1 second overall. And of course, you can configure how long you want it to take. And then you can use Go test command line tool, which will run your micro benchmarks and produces a bunch of output. And we are mostly interested in the number printed in bold, which is the final number of iterations it took so that the overall computation takes exactly 1 second. So let's see how we would, and of course you also get a bunch of other information that we don't really care about. For example, the number of CPU cores that was used. But we are mostly interested in how you would execute those micro benchmarks in the cloud. So let's say you have a couple of micro benchmarks, 3 in this example that you want to execute. And what you might want to do is you just put all of them in a virtual machine, just execute all of them one after each other. But of course, then you kind of have order effects in there, maybe. And you also might have a virtual machine that has weird performance characteristics. So what you do is you just repeat this a couple of times with different virtual machines, and you also change the order in which you execute the micro benchmarks. And in this paper, we wanted to see whether we can use FaaS to execute those micro benchmarks instead, which of course has a better scalability and elasticity than just using virtual machines, but also the execution environment in FaaS is also more variable, and we have some other issues there as well. So yeah, if we just take the same 3 micro benchmarks that we want to execute, instead of executing all of them inside one virtual machine, we just start 3 function instances to execute those micro benchmarks. And if we want to collect more data, more than 1 micro benchmark run, essentially, we can just reuse those function instances to execute the micro benchmarks again. Or we could also just start more function instances and execute all the micro benchmark iterations that we want to have just at the same time, essentially. And of course, if you limit your parallelism, you get fewer cold starts, which might be beneficial because cold starts take a long time and are very expensive. But of course, it's also faster if you just execute all of them at once. So yeah, what's actually inside of the function that we deploy on the FaaS platform? And we have the 2 versions of the software that we want to compare against each other, because we always need to execute the 2 different versions inside of the same function instance, and we can only really take the difference of performance inside one instance into account in our evaluation data. And of course, we also need to compile the source code. So we need to have the Go tool chain inside of our function, which I think is quite unusual. And we also have some issues with caching, because if we just, the cold start would basically take forever if we had to build a new cache for every function instance. So we actually ship a pre-populated cache, and then we have a small wrapper around that, essentially, that just takes care of everything. So in our evaluation, we basically compared this approach to a VM-based micro benchmarking run that we had from previous work. We did some math and basically figured out, yes, they're comparable with each other. You can use FaaS for that. And if you're interested in the details, we have a preprint out on arXiv. The paper is currently being reviewed. Thanks for your attention.
Perfect timing. Thank you,
Bam.
Trevor.
Thanks.
Arshia, can you share your screen?
If you can hear me well, I will just...
I can hear you. I can see your Parrotfish slide. It looks great.
Yep, great. So let's start. Hello, everyone. This is Arsha from UBC, and on behalf of my team, I wanted to present our work and our tool, Parrotfish, an advanced multi-objective serverless right-sizing tool. So let's get started. One promise of serverless is removing the burden of the infrastructure management from the developers. But one of the still remaining infrastructure management choices in serverless is the amount of resources allocated to your functions. This will impact your performance and the cost of using a function. So in almost all cloud platforms, you are charged a constant request cost that you pay for every request, and various capacity cost that depends on the execution time and the resources you're allocated. In AWS Lambda, for example, like the formula is the memory, and like every other resource is basically proportionate to the memory and your execution time. So if you allocate more resources, the cost of the resources allocated to you will go high because you have more resources, but you would expect your execution time to go down because you have more resources. So where is the sweet spot? And this is actually a problem that people care for. We have a lot of blog posts and tools that try to right size and reduce the cost of your of serverless functions. But all of these tools and solutions basically fall into three broad categories. First, we have like the good old manual sweep. You have basically you manually try different configurations, choose the one that fits your needs. Then we have automated sweeping tools that basically they are just manual sweep, but it's kind of automated. So you have a set of predefined configurations and you just explore those and find the best one. We have AWS Lambda Power Twinning that does that. That's a famous tool for right-sizing serverless functions. The problem with like sweeping basically is that the search space can be really huge. And also it's really not efficient, especially that the serverless functions are ever-changing. A bit of a more intelligent approach that we have seen in research mostly is machine learning and techniques like Bayesian optimization that try to model the performance of the serverless functions by looking at it as a kind of a black box approach. So we decided to take a kind of a different approach with the idea of knowing the underlying behavior of serverless functions. We can find the per function performance models using very few samples in a process that's known as parametric regression. So we conducted a test using 7 serverless functions as our benchmarks. We had various language runtimes and characteristics, like we had short-running functions, long-running functions, CPU-intensive, IO-intensive, and so on. And we identified certain family of mathematical functions that can model the performance of serverless functions, exponential being the best and the most consistent one. So does this modeling actually work? The answer is yes. With this kind of white box modeling, we can reduce the exploration cost. This is the cost to get to the optimal solution, the optimal configuration, by 2 to 9 times compared to state-of-the-art tools. And exploration cost is especially important in the face of the ever-changing serverless functions. Like another promise of serverless is faster time to market. So we would expect that code to be changing quite fast and the code updated regularly. And as for the cost of the suggested memory, this is the cost that the developer has to pay for the use of the function at the end of the day. Our tool can reduce that by 25% on average compared to other tools. So we developed a tool using this white box modeling, and our target users were developers, cloud providers, and researchers. Our tool currently supports AWS Lambda and Google Cloud Functions, but we have designed it in a modular fashion, so adding support for other cloud providers is not a hard task. And although we do optimize for cost, but having this performance model of the function allows us to do more than just cost optimization. So as a kind of a prototype, we added support for richer objectives, such as you can put like a maximum on a cap on your execution time. You can define a cost tolerance window that will maximize the performance of your function, like within a window of the minimum cost. And so for more details on the implementation and design of Parrotfish, you can read our paper that was published in SOC 23. And you can start right-sizing your functions by heading out to our GitHub repository. You can find like all the documentations and sample functions and configurations that you can use. I'll post the link to our paper and the tool in the Discord as well. Thank you.
Thank you. Great. And again, questions, I think, ask in Discord. There is a thread you can use.
Yes, I'll be happy to take the questions on the Discord.
Martin, can you share your screen? Yes, looks
Can you
good.
hear me?
And I can hear you. Go ahead.
Okay. Yeah, thanks for the opportunity to address the community here. My name is Marcin. I'm a postdoctoral researcher at ETH. And for the last 3 years, I've been running and leading the project of SeBS, the Serverless Benchmark Suite. We began this work to give the community an open and reproducible platform for measuring the performance of different serverless systems and their features. We focused on making sure that our platform is cloud agnostic, meaning that every benchmark, every application we run has a single implementation that will later map to different cloud services, just to ensure that we can find out where the performance comes from the application itself or the specific cloud interfaces. We target the common languages like Python, Node.js, but also we develop benchmarking C++ because we also want to do high performance on serverless. Finally, we made sure that all of the experiments are very easy to reproduce, so everything is built in the same way, always with the same installation packages, and we make sure that everything is automatic, such that the user doesn't have to configure a lot by themselves, to also diminish the probability that they will introduce some variation to experiments. We deploy all of the benchmarks automatically to the cloud or to different systems, both open source and commercial ones, just to make sure that we can later execute different experiments. What makes us very happy is that we see that researchers are using this to benchmark their research solutions to different benchmarks, different platforms. In the end, benchmarks are there to serve. The important part is that we can help the community to provide reproducible and comparable measurements across different systems. And we are continuing the development, also trying to address what has been going in the serverless community. We have seen that more and more functions that require communication, they move a lot of data. They do machine learning training, data analytics, where a lot of data has to be moved. So we added experiments that can target different communication channels in the cloud and compare them in terms of performance and cost trade-offs. We saw that more and more systems are now using workflows. We analyzed dozens of different papers, and while we find many interesting ideas in the field of serverless workflows, not many papers actually use similar workloads, let alone the same benchmark. We only could find few examples. Therefore, we developed a platform agnostic model for serverless workload, implemented for the three dominating commercial platforms, and allow users now to run the same benchmark in a compatible way on different platforms and make accurate performance measurements. Finally, we also looked into detailed profiling, for example, to allow users now to find where specific bottlenecks might be happening in their functions, for example, specific I/O calls. Serverless is still moving forward. We also see it today with many new exciting ideas, and we are trying to address it as well in our benchmarking suite. So we deploy, particularly this summer, working with our students through the Google Summer of Code program. We want to target now larger, more applications that consist of many functions, and we can synchronize not only this workflow that can be very static, but applications like microservices. We are adding support for new platforms. The fusion is almost done, and we also hope to have a support for Knative soon. If you find some other exciting commercial open source platform for which you want to be able to run your benchmarks, our benchmarks, in an automatic reproducible manner, let me know. We are happy to work on this and work on this together. We are adding support for experimenting with serverless GPUs, examining the trade-offs of sharing and performance. These days, everybody wants to do machine learning. People are using serverless to help machine learning. In practice, you need GPUs for that, and this comes with a lot of new interesting challenges. And we're also looking into the long-term performance stability, so developing experiments and measuring how to understand the variation of performance and really what is causing specific performance outliers over the time. Now, we have seen also today that a lot of new things are coming for serverless, and there are many unanswered questions about the future. I mean, what kind of runtime will be running? Maybe we'll all be in the future running WASM functions across all platforms. We don't know what are the limits of scalability of serverless functions. In practice, if we want to run machine learning trainings, we need thousands of functions. Do we know if the current runtimes will scale up? Now, we don't know what kind of programming frameworks will be needed such that we can develop applications in an agnostic manner. And finally, as we have seen in the keynote, serverless doesn't have to be function as a service. It can be something much more. It can mean much more powerful programming models. We don't know yet which runtimes, which solutions, which ideas will win. But whatever is going to happen to this field, we know that we will need a reproducible, automatic, and user-friendly way to benchmark those solutions and be able to compare across solutions. We believe that our field needs a new and open standard that can incorporate all of the changes that are happening, and we hope that our work, that serverless benchmarks with SeBS, will be able to help with that. You can find more details in our paper. There's also another paper in submission that we hope to publish soon. And of course, all of the details are in our repository. So please try it. If it breaks, let us know. We'll happily fix it. And if you have any requests for features, we're also happy to discuss this. Thank you.
Please, Martin, also share those links in the Discord channel in your, thread. I think it will be much easier.
Absolutely, I will.
From the slides. And then last talk in this session, Bud Taylor, can you share your screen? Okay, I can see your screen. Go ahead. I cannot hear you if you are speaking.
Okay, can you hear me now?
Yes, now it's good.
Okay. Hello, my name is Milt Staler. In this talk, I will discuss Cylon, a high-performance data engineering system, and our research thus far running Cylon on serverless AWS. The data science domain has expanded monumentally over the past few decades, with the main drivers being big data revolution and machine learning. While data processing is an important component of data engineering pipelines, it is also sometimes a bottleneck to many applications. According to the State of Data Science survey by Anaconda, a significant portion of developer time is spent on data exploration, pre-processing, and prototyping. Therefore, it's crucial to improve performance and scalability in data processing. Cylon is a high-performance C++ kernel with a distributed runtime for big data processing, supporting operator parallelism. BSP execution involves concurrent computation, communication, and barrier synchronization to prevent deadlock. It also follows a single program multiple data computing pattern. It uses Apache Arrow, a columnar data format, as it is fast and efficient at processing analytical data. It uses collective communication operations as its main communication pattern. The core data structures exposed to users are data frames, columns, and scalars. It has two levels of procedural abstraction, which are the different operators and communication operators. For serverless Cylon, we use the open source UCC library for collective operations and the open source UCX communication library for high performance communication. Also for serverless Cylon, we use Redis for configuration and barrier synchronization. We use UCX to get MPI semantics without the MPI run engine. Any serverless implementation would also want to avoid the MPI engine, so it is best to find Cylon communications and map optimally on serverless, Kubernetes, and HPC Slurm. This slide describes Redis process initialization. This initialization includes collecting communication metadata required by the communication frameworks, which are world size and rank. In addition, each process also needs the endpoint addresses from each other process. So world size is provided by environment, and for rank, we retrieve it using an atomic increment operation in Redis. We have conducted experiments on both AWS, ECS using Docker and AWS Lambda. This slide outlines our novel approach to high-performance serverless data engineering on AWS using serverless compute. This architecture uses a Cylon scheduler, storage, a fleet of AWS Lambda functions, and a rendezvous server deployed on an ECS Docker container. The scheduler uses AWS step functions for workflow orchestrations. A typical experiment using this infrastructure follows. First, the user executes a step function. The initialization function readies the environment and ensures the Redis key value store is available. As was mentioned earlier, we use Redis for system configuration and barrier synchronization. Next, a Lambda payload is generated as an input for the function. To facilitate scaffolding and invocation semantics on AWS serverless compute, we leverage embedded UCC UCX, and this is included as part of the AWS Cylon runtime. Based on the AWS Cylon payload, we can invoke in function. The UCC UCX infrastructure handles communication between Lambda processes and was described earlier. One solution cited in the research is to leverage NAT traversal via hole punching to enable functions to communicate directly with each other. From a high level, this requires each function to communicate with an external service, which is the rendezvous server I mentioned, to determine the function's public IP address and port. In this case, each function tries to establish a connection, and after a few retries, communication is established. Our AWS Lambda function is packaged as an AWS Lambda container. By using Lambda containers, we can also bypass the size constraint that is imposed for Lambda code on AWS. Our Lambda architecture also includes a mechanism where scripts are sourced from an S3 bucket. This allows us to leverage AWS Lambda execution and separates the Python code from our runtime. Finally, we conducted a series of experiments across nodes for AWS and Ravana, UVA's HPC cluster with 8,000 rows to measure raw performance on these systems. These set of experiments compares AWS ECS Docker containers, which are loosely derivative configuration at UVA's Ravana HPC cluster. Based on our experiments, we can conclude that as the number of rows increases, Ravana's performance begins to converge with AWS strong scaling performance. We hope you enjoyed our talk. If you're interested in the Cylon project, reach out to me on Cylon Data Cylon on GitHub, via email on this slide, or through Discord. Thank you very much.